Hello. Hi guys, good morning. Welcome back to new video. Ki hal chal? Aap doing good. In this, we're gonna see problem letter tiles possibility. Again, we will see three variations, or you can say three approaches for the same. It simply says that we are given n, yeah, right, and that is the tiles which I have, and it's a string where each letter is represent. Okay, what is printed on that specific tile? I have to return the number of possible non-empty sequences of letters which we can make using these letters which we have. Now, technically, let's come up and let's see how we will make it. In general, what we say about sequence is it can be anything. But if we look at this example, they are referring, okay, firstly, the sequence can be single characters, which is A, B. As you can see, I can have A, B. But they have only written A once and B once, which means that another A. Both these A's are technically same. That is the reason I have to only consider this specific A. Okay, then they have another sequence as AA. As you can see, AA. Then I have AB. Okay, AB. But there's one A, one B also, but that is not considered because it is already there. So you already can see that I have to maintain some data structure which can identify the uniqueness of a specific sequence which we have seen so far. So that data structure can easily be a unordered set. Now why unordered? Because I don't want any ordering per se, but I just want the uniqueness factor. So this will help me to give the uniqueness to the string or the sequence which we are generating. Okay, let's proceed forward. Then I have AAB. AAB I have. Then you will see also, but you saw one thing, they also have BA. So this also indicates that I can have a permutations as well. I can have permutations as well. This is something different in this question because technically whenever someone refers sequence, they might be referring ordered sequence. Okay, if the string is like this, just get me the ordered sequence. But no, they want the permutations as well. That is the reason they also have a BA. You might ask, Aryan, why not for this? Because AA permutation will be AA itself, which is same. That is the reason for AA it is A itself. But for AB, I have BA as well. Same way, for AAB, I can have three possible options, either ABA or BAA. That also they are considering. Cool. Let's see now how we will make that. Again, we realize that we have to generate permutations. We have to make sure that the strings are correspondingly unique. Now, make sure before we proceed forward, the like target of this video is 100 likes. Please let's like that. And again, a lot of love for the last videos. You liked it around 200. So yeah, that's pretty great. Now, coming on, we know that okay, at every place I will have an option to choose from. So if I have a, okay, I can choose a, right? Then you might, again, I'm just trying to generate all possible permutations, which means at every index I will go and say, can I use you or not? That's it. Then I can also say, take the middle A, or I can say that, okay, take B. Again, you will see that I have got the corresponding permutation so far also, although you will put that into a uniqueness thing and it will only give you A and B, this A and this B, but still I am trying to generate all possible and then I will put it in my unordered set to get the uniqueness. Why I can do that? Because my length is very small. I can easily generate all possible stuff. So I'm technically going on to all the indexes. Indexes are 0, 1, 2 and then trying to generate it. Okay, let's proceed forward. I went on to the first index. Let's say I took this. Obviously, I have to check if something is used or not, which means that next time I want to generate further. So I will check, okay, I have already taken the 0th index, but not the other indexes. Okay, take them. So what I will do, I will take this A. So this A which I have, let's take in blue color, and then another index which I have not taken so far. So I can take another A, or I can take the same A, or I can take another B. So this is how I can make it, right? This is B at index 2 and this is A at index 1, right? So which ultimately also tells us that I will take an unordered set just to maintain the uniqueness of all the sequences which I am making. But at the same time, I will have a used index kind of a vector which will tell at every point in time what all indexes I have used and what all I can still concatenate, or you can say put up. Okay, let's proceed forward. The same thing I can do it at this step as well. For this A, I can take the A at index 0, okay, and for this A, I can take a B at index 2. Same way, for this B, I can take a at index 0. For this B, I can take a at index 1. Great. Again, you will see that there are a lot of duplications, but no worries. My unordered set will handle everything. Now let's proceed forward. Now I have this AA. The only remaining thing was B. I will attach it. Okay, I will attach that B. Same way, I have this AB. I have one thing remaining, which is A at index 1, which is remaining. Okay, I'll attach that. Okay, let's proceed forward. I have this AA. I will attach a B. Okay, I have this AB. I will attach a remaining A, which is at index 0. Okay, let's proceed forward. I have this BA. I will attach the A at index 1, and I have this BA, I will attach A at index 2. So this is how I can form. Now again, if I see the uniqueness, I will have AAB, ABA, and then BAA. I have BA, I have AB, I have AA, I have A, I have B. So you will see that I will keep on pushing these current sequences in my unordered set, and when the entire tree is done, I will have all the corresponding sequences in my answer. So what will be the complexity? We will see that, but before, let's see the code quickly. So firstly, I will have a unordered set which will say, okay, uniqueness sequence. Then I will have is used just to tell what all indexes are used and what all are not. By default, no indexes are used. Then I know that I can solve it via recursion as well, but I will use backtracking because I know that how I will go about it. Okay, I will go down and then I will simply remove B. Then I will try for next possibilities. Then let's say if here we have, I will remove correspondingly A, then I will try for B. Now if you don't know what backtracking is, no worries, just come on to codegarden.com, just go on to the homepage, crash course, come down, go and check for backtracking. Come down, this is a backtracking crash course. Again, this is not big, it is a part of single video itself, which we have covered everything from scratch, the entire backtracking, right? Okay, the backtracking entire essence is that it helps you to iterate on all these things very easily and very fast. Okay, coming on back, I will have calling this recursive function which will do backtracking also internally. We'll see how. Firstly, I told you that as I am getting a current sequence, I should make sure that every time, no matter what, every time I should put it inside my data structure, which is unordered set. I'll put it because I told you at every step I have to put it inside my unordered set at every step, at every stage itself. Then I will go on to all the indexes which have not been taken so far. I will take that index, which means I will insert that specific character into my sequence. I will call my recursion for next set of characters, but while I am coming back, I will remove that character because now I don't need anymore, and I will also remove and say, okay, it is not also used anymore. This portion is a part of backtracking. Backtracking simply says while coming backwards, simply remove things. So while coming back, I will remove a and then go on to B. I could have used a recursion here as well, which means that I will maintain by simply saying, okay, just update the current sequence with the upcoming cut, which is tiles of index. But because of this, the time will be higher because this operation will take O of n time while this operation takes O of 1 time. Cool? And that is how you can leverage backtracking to optimize your time. Again, if you don't understand what time optimization is, just come and watch the crash course. Just these crash course videos. Now, what is the time for this? Obviously, you will see that at every point, I have three options. So, at every point, I have three options here. Next point, I will have already, if I have three options, I will have only one options now. Then I will have only one option. So if I have n characters in my string, to place at the first location, I have n option. Right? As you can see, I have n option. The next time I have only two options. Next time only have one option. So next time I will have n minus 1 option, then n minus 2 option, and so on and so forth up till 1 option. This is nothing but n factorial. That is the reason we will see our time complexity will be O of n factorial. Now, obviously, you will say that, okay, if I would have taken current sequence plus tiles, which means I would have not used this line and I would have not passed this by address, else right, I would have passed by a value, then it would have been current sequence plus tiles of index. In that case, it would have been n factorial into n. But obviously, we are using backtracking just to optimize the time. We are going ahead with n factorial. And obviously, it's the recursive depth can at max go up till how many characters I have. As you can see, A, B. So it will be O of n. That is my recursive depth itself. Now, can you optimize this? Although O of n factorial for a n of 7 is around 5000. That will completely work. But can we optimize it? Yes, we can. Because if we see this problem again, what it is? It is simply, again, if you just look at it back, then you will realize, sorry, it was AAV. You will realize that it was same as generating sequences, but with a catch that now the permutation also were there. If I give you any sequence, let's say ABA, again, I'm giving you a specific sequence, let's say ABA. I ask you how many permutations for this will be possible or not, how you will find that? It is simply nothing but 3 factorial, because I have three options. So I have three options to place. So to place three options, I will have 3 factorial. But out of these three, how many are same? Two are same. That will be 2 factorial. So this is how, let's say if I have n balls, right? If I have n balls, and let's take, okay, n balls, and let's say these k1 balls are of blue color, k2 balls are of pink color, and k3 balls are of green color, and total, let's say they are n number of, let's take white, total they have, let's say, n number of balls. So number of ways to have a permutation will be n factorial divided by k1 factorial, k1 factorial upon k2 factorial upon k3 factorial. This is the total number of ways I can permute these many number of balls. Now, if you don't know about basic maths and permutation, and if you are a bit weak in that, no worries. Come on to the practice problem sheet. Again, come on to TSA sheet, practice problem sheet. In that, you will find maths and number theory. We have a lot of problems. Usually, you will get all these covered in the medium category itself. Coming on back, we know that now we can use permutation to just permute it now, which means that only I have to find A, B, AA, AB, AAAB. That's it. For AAAB, the permutations will be 3. For AB, the permutations will be 2. For this 1, for this 1, for this 1. So I have 1 plus 1 plus 1 plus 2 plus 3. That's my answer. Which means that I now have to generate just the permutations. Obviously, as I told you that if I have, let's say, if I have reached a specific length and a specific set of characters, for that only I am finding a permutation, which means that AAB. For this, I told you the permutations are 3. How 3? 3 factorial because I have 3 divided by 2 factorial because 2 are same. Now, this gives me 3 as a value, which ultimately indicates that for AAB, my answer is 3. Now, I have to do it for all of them. So if you remember in the very back, I have to take single character also, double also, but in double as well, I can have same as well as different. So again, this is more about that for a specific set of characters, I can have one permutation, but still I have to figure out all possible set of characters. How I can do that? Simple. Take your take your simple approach of take not take. If I would have asked you, then you will say, okay, at every index I have two options. Either I will take it or not take it, take it or not take it, take it or not take it. That's how you generate sequences, right? Only sequences. That's a simple. If I ask you generate all possible subsequence, you will do okay, take not take operation. Now let's do the same thing. If I take it, right, okay, let's take it, or else if I don't take it, okay, take it, okay, what else if I don't take it, okay, empty. Okay, let's proceed forward. Now again, as you take it or not take it, make sure that you are updating your corresponding unordered set as well, because here in this case also we will need that. Okay, now let's proceed forward. Now we are at the next index. If we take it, let's firstly put it a and then a. What if I take it, which means this specific a? Okay, if I take it, great. If I don't take it, it is empty. Okay, now for this also, if I take it, let's say if I take it, again put it up with blue. If I take it, which means this a will come up. Okay, if I don't take it, again it's empty. Let's proceed forward again. I have a. If I take b, okay, take b. If I take now a, sorry, yeah, if I don't take it, then obviously it will be a only. Then again let's proceed forward. That okay, if I take it, a, and then one is empty, which means I am at b. If I take it, okay, b. If I don't take it, only a. Okay, let's proceed forward. When I have this underscore, if I take b, okay, it will be a b. If I don't take it, it will be a. For this case as well, if I take b, it will be b. If I don't take it, it will be empty. So you will see that I have generated all possible subsequences. I have a, I have b, I have ab, I have aa, and I have aab. Make sure that these are just the subsequences. They have not yet included the permutation. But I easily realized that at the final level, I will be able to generate all possible subsequences. I just have to make sure that I will put all of them in my unordered set. Again, you see one thing, that in the last stage itself, you are able to get all possible subsequences. So you will just put up all of them into an unordered set, and thus you will get uniquely these all subsequences. Make sure that you have to take their permutation also in consideration. Now I will find their permutation. So for it will be 1, it will be 1, it will be 1 only. Sorry, it will be 2 because I have 2, so it will be 2 factorial upon 1 factorial into 1 factorial, right, which is nothing but 2. Here itself it will be 2 factorial divided by 2 factorial, which will be nothing but 1. Here itself it will be 2 factorial, sorry, 3 factorial divided by 2 factorial into 1 factorial, which is nothing but 3. So that's how 3 plus 1 plus 2 plus 1 plus 1, 3, 4, 5, 6, 7, 8. 8 will be my answer, and you can also see that 8 was my answer. Cool, let's proceed and show you the corresponding piece of code. Again, I hope that you guys got the math behind it, and also it's a simple recursion of take not take just to generate all possible sequences. So firstly, as you know, I'm generating the factorial. Although the factorial will be of size n, that is the reason. That's not a very big deal per se here to generate it or pre-compute it. I have done pre-computation, although it's not necessary. It will not impact much of your time. But still, we have done the pre-computation. Again, factorial simply says that any number n, again, if you don't know about factorial, again, I highly recommend go and watch the maths practice problem playlist. You will get that. That's a very common stuff which we do. Now, coming on back, we will come on to the main function. As you see that I have again have an unordered map, unordered set here. Just just to get the unique string. But again, in this case, I will put sequences when I have reached the last index. Now I will sort it. Now you might ask, Aryan, why are you sorting it? Technically, you will say that is, yeah, might not be required in this case, because even if I just get it for ABA, even if I get it for ABA, that also will give you the same set of results as what AAB gave. Even in the end, I will have to do permutation, and permutation will not, differentiate between this and this when I'm computing the final answer. So yeah, sorting would not be required in this case. Right? Again, if you guys want, I can have a quick correction as well and check that if it's working or not. Technically it should work, because whenever we apply sorting, okay, CDC, CCDC, CC, okay, let's take that example quickly and see that CDC. Now if I will sort it, it will become a CCD. But if not, then at every point in time I will have two options: either I will take it or I will not. Now if let's say I take it, great. If I don't take it, okay, it's empty. If I take it, then it's C, and then if I don't take it, then it's D. Oh sorry, if I take it, then if I don't take it, if I take it, then D. If I don't take it, then it's C. Then here also I have another set, which is take it or don't take it. Then here as well, I have D, C, C, and here, let's say C, C. Here I have D, C. Here I have, okay, got it. So you will see that why sorting is required here in this case. Sorry, I missed that. That's pretty much evident because, okay, let's firstly complete this because you will have a D here, and then you will have a C here, and then nothing here. Okay, maybe I missed some things. It will have a CD as well. So you see that my permutation will end up counting CD and DC because I will do a permutation, so I will get something extra. That is the reason you will see the output is 10, expected was 8. Why you are getting extra? You are getting extra because you are actually, you made this, but ultimately, because of C, also later on, technically, it also is generating a DC, which means that you will make permutation of this as well, along with this as well. While when you would have made a permutation of this, it would have automatically been made. That is the reason sorting is required in this case. Yeah, that's primarily important because you want one set of characters at one, collectively together, then another set of characters, because your program will make sure that okay, you are putting up cd. It will never put up a dc because dc is a job of permutation and not your sequence generation. Cool. And that is the primary reason we will have to use a sorting. Okay, my bad. Actually missed that, but yeah, that's the entire reason for sorting. Now we will just do a pre-computation of the factorial, which is computing this, and then I will call my generate sequence function. Now this sequence function will simply say that, bro, make sure that you take not take, which means that if I don't take the current character at this position, okay, move on to the next position. If I take that, which means current plus the tiles, then I will simply take that and go on to the next location. This is exactly same as what we also discussed above. Just simply we have two options at every point in time, take not take. Now again, because we have two options at every point in time, you will easily see that our time complexity will also be 2 raised to the power n, because we have two options at every point in time. Now coming on, let's proceed. If we have a base case will be if I have reached the end, which is, you see, the last line. If we have reached that last line, then I should make sure I will check. If I have already seen that, then you should return a 0. Please don't count it again, which means that in this case AB was already seen. When I will be computing that, and I'm at last line, AB is already seen, A is already seen. So please don't add that. That is the reason I will use my unordered set for that, and check if it's already seen, simply return a 0. If not, then put that in your scene vector and make sure to count the permutation of that as well, because for you the permutation of this is important and not just the subsequence. Okay, and then we can simply end it. Now you will see that just to count the permutations, I've done the exact same thing. I will count the characters, and what all are same, I will divide by their corresponding, factorial, which means if I have n characters in total, in which k1 are same, k2 are same, k3 are same, I will simply do a n factorial, which is total factorial, factorial of the entire length, and then dividing by k1 factorial, k2 factorial, k3 factorial, and so on and so forth. And that will be my total number of permutations which I can have. Now what will be the complexity for this? Obviously, because of this piece, you will have complexity of 2 raised power n. But as in the last step, which means for each and every sequence, what you are doing, you are firstly checking that in your unordered set, that's okay. Then you are finding the corresponding permutation. For finding the permutation, you are iterating on the entire length of that specific string. Because of iterating on the entire length, you are taking the O of n time. You are taking O of n time because of iterating on the entire length. Along with it, because here in this case you are saying that you are passing your current as a string and not as an address, that will also be taking O of n time. Now this portion will take O of n into 2 raised power n time, while for each and every string in the final end, which means at the final answer, each and every string will take O of n time because of this count permutation, because of this iteration and finding the frequency. So it ultimately indicates that at each step, I am taking O of n time, right? But in the last step, itself, I am taking n time extra. That is the only catch here. So the time is still n into 2 raised power n, because this is going to be happening for only the last phase of my recursion. That is the reason my time is this. And obviously recursive depth will be O of n. Can I optimize this? Yes, I can. But will the time improve? No, it will not. Because I can optimize this by passing this thing as a form of a backtracking logic, as we have seen previously. With that, this piece of logic, which means this n will go away, but still this n will still remain. If this n still remains, obviously it indicates that for the last point where I have generated all 2 to the power n sequences, I will still have to have that O of n. And that is the reason I can improvise that. The improvised logic is nothing exactly same. It's just that just doing a O of 1 operation of putting a character and then using backtracking to remove it again, O of n. Now I'm passing current with the help of my reference. But again, as I mentioned, this will take O of n time for all these sequences in the last phase, of my recursion, which is this specific phase. And that is the reason my time is still O of 2 to the power n into n. But the only catch here is this process will take O of 2 to the power n time only, although again this will again still take O of n time. Cool. That is how you can improvise that. But again, time on paper is still same, but still it is a bit faster. Bye bye. Take care. I hope you guys got it. Make sure that you do check out the practice problem playlist. Bye bye.